Okay, in this lecture video, we're going to look at the energetic changes associated with a sodium cation glucose pump. Okay, and we're going to look at the calculations, how much energy it takes for these transport mechanisms, and the resulting glucose concentration that we can build up inside the cell. So this is going to be a pump that utilizes a sodium cation electrochemical gradient to bring lots of glucose into the cell. So normally, if you're going to bring glucose into the cell by passive diffusion, it could only come in until the concentrations on both sides of the cell have equalized, right? Then the flow would stop because there's no driving force. So in active transport, we can utilize the electrochemical gradient from an ion to actually bring in extra glucose so that you can get more glucose inside the cell. So in this example, we're going to look, we've got 145 millimolar sodium concentration outside the cell. So this is my cell. This is outside the cell, this is inside the cell. And this is how I think about all of these types of problems. I always start out with a sketch so I can keep track of what concentrations are on what side of the cell membrane and the direction of my solute flow. So in this case, I've got 145 millimolar sodium cation outside the cell, and I've got 12 millimolar sodium cation inside the cell. So the way this particular pump works is it's going to bringing ions and glucose in. So it's going to bring 2 sodium cations in for every single glucose molecule that it brings in. Okay, so if we look at this just in terms of sort of conceptually, we can see that if sodium is going to flow from a region of higher concentration to a region of lower concentration, that's going to reduce the electrochemical potential. So we're going to get that difference in energy that can then be harvested to drive glucose against its concentration gradient and bring lots of extra glucose into the cell. So in this problem, we're going to figure out if you bring in 2 moles worth of sodium cations, how much glucose can you actually bring in? So we can look and see how we build up this concentration gradient. So the first thing I do with these problems is I draw my sketch so I can keep track of what's where. Then I write a chemical equation so I can keep track of where we're starting and where we're ending. So in this case, we're flowing from outside the cell to inside the cell. The other piece of information that you need to know is the transmembrane potential. And that would be given to you. So it is 50 millivolts, so that describes the difference in charge across this membrane. And the inside of the cell is negative relative to the outside of the cell. So it's more negative inside the cell compared to the outside of the cell. And this is going to be important in figuring out the sign of the transmembrane potential as you go to calculate your delta G. And we'll go through that. Okay, so now let's take a look then at our expression for delta G. So delta G equals RT natural log. So we're talking about finding out how much energy is associated with bringing these sodium ions in, because we're going to use that to figure out our glucose concentration gradient that we can build up. So RT, concentration of the sodiums inside the cell, because that's my final from my little chemical equation I wrote. That's the end where we're going to end up. Divided by the concentration of sodium outside the cell. So there's my concentration component, plus ZF delta pitchfork. So sometimes you'll also see Z represented as N, but it's still the charge. So what I can do is I can look at these two terms and I can think about how they should end up based upon what I know conceptually. So for example, when I look at this concentration term, I know that when I do this calculation, the end result should be negative. I should get a negative delta G contribution because sodium is going down its gradient. So there should be a negative free energy associated with that. So we're going from 145 millimolar to 12 millimolar. Then I can look at what I think my charge contribution is going to be. So I know that I've got more positive ions outside the cell compared to the inside the cell, because I said that the transmembrane potential is more negative inside the cell. So if I'm moving a cation from outside the cell towards that negative charge, then I know that my charge contribution should also give me a negative free energy contribution. So in both of these cases, I'm going to have a negative chemical component and a negative charge component, giving me an overall negative component, or a negative value for my delta G of moving those sodium cations. So then let's look at what this is going to turn out as. So then we know delta G, if I wanted to plug all these numbers in, would be 8.315 joules per mole Kelvin. I think I'm going to wish I had a regular iPad at this point. Let's do this at body temperature, so 310 Kelvin for my temperature. Natural log of 12 millimolar divided by 145 millimolar. And I like to just go ahead and convert these all to molarity. That way I don't get messed up in case I have some other complicated transport mechanism. So there's my chemical contribution. So then I'll do my charge contribution. So Z, the charge on a sodium cation, that's +1. Faraday's constant, 96,480 joules per volt mole. And now I can take a look at what my transmembrane potential is going to be. So I'll tell you for now, just so you can write it down, it's going to be negative 0.050 volts. Okay, and so there are a lot of different ways that you can think about what that sign should be. So let's go through that. So we know that we're going from outside the cell to inside the cell. So the difference in potential, electrical potential then, would be the potential inside the cell minus the potential outside the cell. So since you know that the inside is negative relative to the outside, we could write it like that. So a negative minus a positive will still be a negative value. That's how I knew that I should be including a negative sign in here. The opposite version would be, what if I was going, the reverse direction, in to out? Then I would say the transmembrane potential would be the potential outside the cell minus the potential inside the cell. So this is always final minus initial, which would be a positive value minus a negative value if the inside is negative relative to the outside. And a plus minus a negative is going to give you a positive value. So that means if we were moving that would be if we were going the opposite direction to try and move these sodium cations. So you can figure out in your equation what charge to make this. So even though the number might be given to you as a positive value, you need to take a look at what side of the cell membrane is more negative. That way you can use final minus initial to figure out what the actual sign is when you put it into your equation. Okay, so now we know how to do that. So if we come back and do all the math, plug all those numbers into our calculator, we find that delta G equals negative 6,423 joules per mole. And remember, we're talking about per mole of sodium cation here. Plus, so that was our chemical potential, which was negative, like we thought, plus a negative 4,824 joules per mole of sodium cations. So again, we got a negative value for our electrical contribution. You could also think, if you plugged in the wrong sign for the transmembrane potential, let's say you accidentally made it positive, then you would have gotten a positive value for the electrical component. But we already went through it conceptually and said that number should be negative. So then you know you just got to change the sign on the value. So if we add those two together, we've got minus 11,247 joules for every mole of sodium cation that we bring in. But we know in this particular transporter that it's going to bring in 2 moles of sodium for every single mole of glucose. So that means we've got minus 22.5 kilojoules of free energy available for every 2 moles of sodium cation that we bring in. Okay? So that's how much energy we have. So let's see how that's going to relate to the concentration gradient that we can make with our glucose at the same time. So we know that if we're going to free up, we're freeing it up, 22.5 kilojoules per every 2 moles of glucose or of sodium cation that crosses the membrane, then we can use that, so that's why I'm putting a positive sign, positive 22,500 joules of energy for every mole of glucose that we want to bring in. So this is positive because we know we're going to move glucose against its gradient. We're harvesting the energy from bringing in the sodium cations and using it to bring in the glucose. So that's going to equal RT, natural log, concentration of glucose inside the cell divided by concentration of glucose outside the cell. Well, I ran out of room on my iPad. Okay, because again, remember, we're going from outside the cell to inside the cell in our process. So final minus initial. So then we know that R is 8.315 joules per mole Kelvin, and we said we're using a temperature of 310 Kelvin, so body temp. So then you can solve this equation for this ratio right here. Divide both sides by RT and raise them e to the x. And if you do that, you get that the ratio of concentration of glucose inside the cell to the ratio of glucose outside the cell is about 6,000. Right? That's huge. So we're way past the point of equalizing the concentrations of glucose inside the cell versus outside the cell. We've now got 6,000 times as much glucose inside the cell as out, just from harvesting the energy from that pump, from letting those sodium ions flow down their electrochemical gradient.